Is continuous rotation. 4. Artificial gravity power hungry. Imagine floating in space, feeling weightless and free, but also knowing that long-term health needs gravity. That's where artificial gravity comes into play. One popular way to create it is by spinning a spacecraft or habitat. But how much energy does that really take? Let's find out. When a spacecraft spins to generate artificial gravity, it uses centrifugal force to mimic the pull of gravity. Once the structure reaches the right spin rate, it doesn't need a lot of power to keep spinning. In space, there's almost no friction, so the rotation can continue with very little energy input. Think of it like spinning a wheel in a frictionless environment. Once it's moving, it keeps going naturally. Most of the power is used during the initial phase, when engineers accelerate the habitat to the desired rotation speed. This process, called spin-up, can take hours or days depending on the size and mass of the structure. During this time, powerful motors or thrusters are needed to reach the target spin rate. Once spinning, the energy needed to maintain that rotation is minimal because there's no resistance in space. Controlling the rotation is another factor. Engineers might need to make small adjustments to keep the habitat balanced and prevent wobbling. These adjustments requiring some energy, but they are usually small compared to the initial spin-up. Larger structures, like rotating space stations, might need more active control systems, which could increase overall power needs slightly. The size of the habitat also matters. Larger habitats, which are more comfortable for astronauts, requiring more energy to spin up because of their mass. For example, a habitat with a diameter of 100 meters might need several hundred kilowatts of power during spin-up. But once spinning, the ongoing power use drops significantly, often to just a few kilowatts or less. Engineering challenges can add to power needs too. Balancing a large rotating habitat to prevent wobbling or gyroscopic effects can involve active control systems. These systems use sensors and small thrusters, which consume some energy but are not directly related to the rotation itself. Looking ahead, space agencies are exploring ways to make artificial gravity more efficient. Future designs might include lighter materials, more precise control systems, or even alternative methods like magnetic or electrostatic levitation. But for now, continuous rotation is considered quite energy efficient once the habitat is spinning. In summary, maintaining rotation for artificial gravity isn't power-hungry during steady operation. Most energy is used during the initial spin up and for active balancing. The ongoing energy costs are relatively low, making it a practical option for future long-term missions. This approach could help astronauts stay healthy and comfortable on missions to Mars or beyond, all while keeping energy demands manageable.